Okay, let's unpack this. I want you to just take a second and, look around the room you're sitting in right now. Or, I don't know, if you're commuting, look at the road, the bridge you're driving over, the train tracks. We tend to think the modern world is built on technology, right? Or innovation, or the cloud.
But if you actually peel back the layers,
Mm-hmm.
I mean, if you look at the raw inputs that make the concrete stand up and the lights turn on, a staggering amount of it still runs on a lump of black rock.
A simple, dirty, crumbly black rock. You can hold it in your hand.
Yeah.
It gets soot all over your fingers, smells a bit like sulfur, and honestly, it looks completely uninteresting.
Right.
But this rock, coal, is arguably the most paradoxical thing on the entire planet.
It is a massive paradox. I mean, it defines that dual nature of progress better than almost anything else. On one hand, this rock is the battery that powered the whole modern world. It's the reason we aren't all subsistence farmers. It built the cities, forged the steel in our cars, and kept humanity warm through centuries of brutal winters. It completely broke the energy ceiling.
It's the hero of the whole industrial story. But then, on the other hand, it is the undisputed villain today.
Oh, absolutely. The bad guy.
It is the single largest contributor to the climate crisis. So the mission for this deep dive isn't just to rehash the politics, because we hear about phasing out versus phasing down all the time.
Right, we get that.
But to actually look at what this stuff is.
Yes. Let's go beyond the headlines. We need to look at the geology, the chemistry, the deep history. Because when you hold a piece of coal, you are not just holding a rock.
You're holding a time capsule.
You are. You're holding fossilized solar energy from a world that wasn't just different from ours, it was.
Yeah.
It was alien.
Okay, so we've got a massive stack of sources here. Encyclopedic records covering geology, history, economics, environmental science. And I want to start with that idea you just threw out. Fossilized solar energy. Because I think most people have this vague idea that, okay, coal comes from dead plants. Maybe they think of dinosaurs.
No dinosaurs. Not for coal.
No.
Yeah.
No dinosaurs. But the actual process of how a plant turns into a rock that burns, it's way more intense than just plants died and got buried.
It's so much more specific. To really get it, you have to transport yourself back to the Carboniferous period. We're talking 300 to 360 million years ago.
The Carboniferous, the name literally means coal-bearing, doesn't it?
Precisely. And if you stepped out of a time machine into the Carboniferous, the first thing you'd notice isn't the trees.
What is it?
It's the air. The atmosphere was hyperoxygenated. Today, oxygen is, about 21% of our air?
Right.
Back then, it was upwards of 35%.
Wow. Which, that sounds great for a morning jog, but I read that it had some terrifying side effects.
It allowed for gigantism in insects. Because insects breathe through these little tubes in their bodies, spiracles, and their size is limited by how efficiently oxygen can diffuse into their tissues. But with that much oxygen pressure, well, the limits were taken off.
This is the part of the research that honestly gave me nightmares. We're not talking about slightly bigger bugs.
Oh.
We are talking about dragonflies the size of hawks.
Meganeura. Yeah, wingspans of 2.5 feet.
And millipedes. Millipedes the size of crocodiles.
Arthropleura. A 6-foot-long millipede crawling around in the underbrush. So just, keep that image in your head. A hot, wet, hyper-oxygenated swamp buzzing with giant insects. But the stars of the show were the plants.
And these weren't our kinds of trees, right? Not oaks or pines.
No, nothing like that. The forests were dominated by lycophytes. We call them scale trees and giant ferns. They grew 100 feet tall, but they were strange.
How so?
They didn't have wood like we think of it. They had this thick, scaly bark, almost like reptile skin. And they reproduced with spores, not seeds.
So no flowers, no fruits, no birds singing, because birds, they hadn't even evolved yet.
Yep. Just the hum of giant bugs and the crashing of these weird spore trees.
And this leads us to what has to be one of the most fascinating theories in all of geology. It's called the lignin lag.
I love this theory.
It sounds like a band name, but it's really about, tree indigestion.
It's about an evolutionary mismatch. So here's the premise. Around 360 million years ago, plants evolved a new chemical compound called lignin.
Lignin.
Lignin. It's this complex organic polymer. It's the rigid stuff that makes cell walls hard. It's what allowed plants to stop being moss on the ground and start growing, vertical.
So plants figure out how to build skyscrapers, they get tall, they get structural, but here's the catch.
Nature hadn't figured out how to take them down yet.
Exactly.
In a balanced ecosystem, you have producers, the plants, and decomposers, fungi, bacteria. But lignin is incredibly tough chemically. It's like a fortress. And the theory goes that for millions of years, maybe 40 or 50 million years, trees had lignin.
But the fungi and bacteria just hadn't evolved the enzyme to eat it.
They could break it down.
That's incredible to think about. I mean, imagine if we invented plastic, which we did, but there was absolutely nothing on Earth that could break it down. Oh, wait, that's actually a terrifyingly accurate analogy for today.
It is, ironically. But back then, it was all organic matter. So these massive scale trees would grow, die, fall over into these swampy waters. But instead of rotting away, like a log does in a forest today,
It returns into soil in a few years.
just sat there. They didn't rot.
They just piled up.
Layer after layer. For 50 million years, dead trees, perfectly preserving their carbon, stacking up like a giant compost heap that never, ever composted.
And that massive pileup is why we have coal today. If those mushrooms had just evolved a little earlier, the Industrial Revolution might never have happened.
It's entirely possible. Now, I have to add a little nuance here because science is always updating.
Of course.
While the lignin lag is a great story and likely played a huge role, recent research suggests it's not the only reason. There are also massive tectonic factors at play.
Tectonic factors? You mean like the continents were moving around?
Exactly. At this time, the supercontinent Pangaea was forming. All the landmasses were smashing together, and this collision created the Central Pangaean Mountains, a huge range running right along the equator.
So you basically have these new Himalayas popping up in the tropics.
And climate modeling suggests these mountains created a massive monsoon zone. It caused year-round heavy rainfall, no dry seasons.
Which means the swamps just stayed wet.
Right.
Permanently.
And the trees fell into water that was anoxic. No oxygen. So even if there were some bugs or bacteria that wanted to eat the trees, they couldn't survive in that deep, acidic, oxygen-starved sludge.
So whether it was the lag in evolution or the specific swamp conditions from Pangaea, the result was the same.
Right.
Huge amounts of organic matter carbon were buried in mud before they could rot.
Precisely. We basically buried the atmosphere. We took the carbon dioxide the plants had breathed in, locked it in their trunks, and just shoved it underground.
And that buried pile of plants, that's what we call peat.
Peat is the precursor. Step 1. If you go to a bog in Ireland or Scotland today, you can see peat. It's soggy, brown, kind of sponge-like. It's definitely biological matter, but it's not rock yet.
Then comes the cooking.
Yeah.
The coalification.
Yes. So over millions of years, the continents drift, sea levels rise, and sediments, sand, mud, silt pile on top of that peat. The weight is just immense.
Like a geological pressure cooker.
That's it. It creates pressure, and deeper burial creates heat. And that process drives out all the volatiles, the moisture, the oxygen, the hydrogen, and it concentrates the carbon. It transforms the material from a biological sponge into a metamorphic rock.
And this is where we get the different ranks of coal, which I think is so important because we just say coal, but not all coal is created equal.
No, it matters immensely. If you're a utility company or a steel worker, the rank changes everything. Think of it as a spectrum of maturity.
Okay.
At the very bottom, you have lignite, or brown coal.
Brown coal. The sources describe it as almost woody still.
It is. It's the lowest rank, geologically young. It can be up to 70% water sometimes. It's a crumbly, low-energy density, and it's arguably the worst for your health when it's burned because it burns so dirty.
Why does it burn dirty? What does that mean?
It's full of impurities. It hasn't been cooked long enough to become pure carbon, so when you burn it, you're boiling off a lot of water and releasing a ton of other chemicals just to get a little bit of heat. It's really the junk food of the fossil fuel world.
But we still burn a lot of it, don't we?
Huge amounts,
Yeah.
especially in places like Germany and parts of Australia, because it's often found right near the surface. It's just cheap to mine.
Right.
But then, if you cook that peat longer and deeper, you move up to bituminous and then bituminous coal.
Bituminous is your standard black coal.
This is the workhorse. It's dense, it's black, usually has these bands of shiny and dull layers. This is what fuels most power plants and what's used in steel making.
And its carbon content is, what, 60 to 80%?
Somewhere in there, yeah.
Mm-hmm.
But at the very top, the VIP of coal is anthracite.
Anthracite, hard coal.
It is. It's glossy, almost metallic looking. It's hard to break. And it has the highest carbon content, up to 98%, because it was subjected to the most intense heat and pressure. It burns with this pale blue flame, very little smoke, and incredible heat.
And there's a rule of thumb for finding this stuff, right? Something called Hilt's Law.
Hilt's Law, a classic geological rule. It generally states that in a given area, the deeper you dig, the higher the rank of the coal you'll find.
Because depth equals more pressure and more heat.
Exactly. So if you find bituminous at one level and you keep digging, you might just hit anthracite.
So we have this biological battery, dead trees, buried, cooked, compressed until they're solid rocks of energy. But humans have been walking on this stuff for a long, long time. When did we actually figure out what to do with it?
That's a great question. We tend to link coal immediately with the Industrial Revolution.
Right. Dickensian London, steam engines, factories.
All that. But the history goes back thousands of years. I saw a note here about the Romans.
Yeah. In Roman Britain, they were digging up something called outcrop coal.
Outcrop coal, yeah.
What is that?
It's just coal that's sitting on the surface, exposed by erosion. They used it to heat their baths, and even for smelting iron on a really small scale.
Yep.
We've found coal ash in the ruins of Roman villas.
But then the Roman Empire collapsed, and Britain just stopped using it for centuries. They went back to wood.
They went back to wood?
Why? I mean, if coal is better, why go back?
Because wood was easier. If you live in a forest, you just chop a tree. It's right there. Mining is dirty. It requires effort. You have to dig a hole. And humanity generally follows the path of least resistance until we hit a wall.
And we hit that wall when in the medieval period.
A bit later, leading up to the 1700s. But there's a famous story in between. Marco Polo.
Ah, yes. The 13th century.
Marco Polo travels to China, and he writes back to Europe just amazed. He described black stones, which burn like logs. He was astonished, and he noted that because of these stones, the Chinese could keep their baths warm, allowing people to take 3 hot baths a week.
3 hot baths a week in the 13th century. That's a luxury.
It was a massive luxury. And he noted that even though there was plenty of wood in China, the population was so huge, they would have run out of fuel without these stones.
Wow.
They'd already figured out the energy density problem.
So China was way ahead of the curve. But the real explosion, the thing that changes the world, that happens in Britain. And it happens because of a crisis.
The resource trap.
Is that what it was?
In a way. By 1700, Britain was running into a huge problem. They had deforested massive parts of the country. They needed wood for building ships. The Royal Navy just ate forests for breakfast and for charcoal to smelt iron.
And just for heating homes.
Right. Firewood prices were skyrocketing. The poor were freezing. Britain was hitting a hard energy ceiling. They simply couldn't grow trees fast enough to support their economy.
They were limited by the solar collection rate of the current year.
Exactly. But they were sitting on an island made of coal. In 1700, Britain was already mining 5/6 of the world's coal. They had to. If they hadn't switched, historians estimate they would have hit a hard limit by the 1830s. They would run out of sites for water mills and run out of wood.
So coal broke the ceiling. It let them access the solar energy of millions of years all at once.
It was a massive inheritance. But there was a catch. As they mined more, they had to dig deeper. And when you dig deep in Britain, or anywhere, really what happens?
Water.
The mines were flooding. You couldn't get the coal out because you couldn't pump the water out fast enough with, horses walking in circles attached to buckets.
And this desperation is what drove the invention that changed everything, the steam engine.
This is a critical feedback loop. Thomas Newcomen and later James Watt, they didn't invent the steam engine to power locomotives or factories. They invented it to pump water out of coal mines.
That is such a rich irony. The machine that launched the carbon age was created specifically to get more of the fuel that powered the machine.
It was a perfect self-reinforcing cycle. The steam engine burns coal to pump the mine. The mine produces more coal. The coal makes cheaper iron and steel. The steel makes better, more efficient steam engines.
Which can then be put on wheels trains or on ships.
And suddenly this rock isn't just a rock. It's the fuel for empire. It's the fuel for speed. And it split the world into geological haves and have-nots.
If your country had coal like Britain, Germany, the U.S., you industrialized. You became a superpower. If you didn't,
you fell behind. And it centralized everything, too. Before coal, you had to put your mill on a river. You were geographically constrained. With coal, you could build a factory in the middle of a city as long as you could bring the rock to it.
And that gave birth to the modern industrial city, with all its wealth and all its smog. Which brings us to the modern era, because we're not just burning it in steam engines anymore. The uses are really specialized now. We need to distinguish between the two main types, thermal and metallurgical.
This is such a crucial distinction, and it gets lost in the general ban coal debate.
Okay, let's start with thermal coal. This is the electricity stuff.
Right. Thermal coal is for heat. The process is pretty violent, actually. The coal gets to the power plant and it goes into a pulverizer,
A giant grinder.
a giant mill that crushes the rock into a fine dust, like the consistency of face powder.
Why dust?
Surface area. You throw a big rock in a fire, it burns slowly. You blow dust into a fire, it ignites instantly. They blow this coal dust into a furnace, creates a fireball, boils water in tubes, creates high-pressure steam, and that steam spins a turbine.
So when you turn on a light switch in many parts of the world, Kentucky, Poland, huge parts of China, you're basically burning thermal coal dust.
You are. But metallurgical coal or coking coal is totally different. You don't just burn it, you bake it.
You bake it like a cake.
You put it in a massive battery of airless ovens, heat it to about 1,000 degrees Celsius, and because there's no oxygen, it doesn't catch fire. It pyrolyzes.
What does that mean, pyrolyzes?
It sweats. It sweats out all the impurities, the oils, tars, methane, hydrogen. And what you're left with is a hard, porous, gray rock called coke.
And coke is just pure carbon.
Almost pure. And coke is absolutely essential for making steel. You mix coke with iron ore in a blast furnace, and the coke acts as a reducing agent.
Okay, explain that chemistry. Why do we need the carbon?
Because iron ore isn't iron. It's iron oxide. It's rust. The iron atoms are holding hands very tightly with oxygen atoms.
Right.
To get the iron, you have to break that bond. You need a homewrecker.
And carbon is the homewrecker.
Exactly. At high temperatures, the carbon strips the oxygen away from the iron to form CO2, leaving behind pure liquid iron. You just cannot make traditional steel without this specific chemical reaction.
And that's why you hear people say, look, we can stop burning coal for electricity, but we can't stop using it for steel.
It is much, much harder to replace in steel production.
Yes.
People are exploring hydrogen as an alternative homewrecker to grab the oxygen, but for now, coke is the global standard.
Now, when we talk about who is using this stuff today, I mean, there's one giant in the room.
Yeah.
The numbers are just staggering. China mines almost half the world's coal and consumes more than half of it.
It's the engine of their manufacturing dominance. While the U.S. and Europe have been retiring coal plants, China has been building them. Although, even there, the dynamic is starting to shift.
Well, let's talk about that shift, because this is where the economics get really interesting. It's not just about environmentalism. It's about cold, hard cash. There's this term, stranded assets.
Right. This is the nightmare scenario for any investor. Imagine you build a massive coal power plant today. Costs billions of dollars. You plan to run it for 40 years to make your money back.
It's like taking out a 40-year mortgage on a factory.
Exactly. But 5 years from now, solar and wind power become so cheap and battery storage becomes so effective that it's actually cheaper to build a new solar farm nearby than it is to just buy the coal to feed your existing plant.
Wait, so the cost of operating the old plant is higher than the entire cost of building a brand new renewable one?
That is the crossover point. And we are hitting it in many, many markets. So your billion-dollar coal plant becomes a stranded asset.
A giant concrete paperweight.
An investment that has lost all its value before its useful life is over. And this is the risk that financial markets are looking at right now. Investing in new coal is becoming financially toxic, not just environmentally toxic.
Banks just don't want to lend money for a project that might go bankrupt in a decade.
Precisely. The market is moving faster than the policy in some places.
Speaking of toxic, we have to go there. We have to talk about the dark side, because for all the benefits coal brought, the hot baths, the steel, the electricity the bill has come due, and the cost is high.
It is incredibly high, and it's not just about future climate risks. It is about immediate human health.
The famous historical example being the London smog.
The Great Smog of 1952. That was coal smoke, just trapping the city. Thousands of people died. But today, the killer is more invisible. We look at particulate matter PM2.5.
These tiny, tiny particles released when coal is burned.
They're less than 2.5 microns wide. I mean, for context, a human hair is about 70 microns. These particles are so small that when you inhale them, your body's natural filters, nose hairs, mucus, they can't stop them.
So they go right into your lungs?
They pass right through your lungs and enter your bloodstream.
They get into the blood.
Yes. They can travel to the heart, the brain. They cause systemic inflammation. This leads to strokes, heart attacks, respiratory disease.
And the stats in the source material are just grim. An estimated 800,000 premature deaths annually globally linked to coal.
And some studies say that's a conservative estimate, and we can't forget the minors. Black lung disease, or coal workers' pneumoconiosis, is still a very real, very horrific way to die.
What actually happens in black lung?
You inhale coal dust over years. Your lungs can't clear it, so your body tries to wall it off with scar tissue. Your lungs literally harden and turn black. You lose elasticity. You just slowly suffocate because your lungs can't expand. And tragically, we are seeing a resurgence of it in some areas, even with modern safety equipment.
There was also a detail in the sources that really surprised me. We all worry about nuclear power and radiation, but coal ash, the stuff left over after you burn the coal, it's actually radioactive.
It is. This is one of those facts that sounds like a conspiracy theory, but it's just basic geology. Coal contains trace amounts of uranium and thorium. They're naturally occurring in the rock.
But trace amounts are harmless, right?
In the rock, yes. But remember, we are burning the rock. We burn away the carbon, the organic matter, which is most of the weight. But the uranium and thorium, they don't burn. They're left behind in the ash.
So you are concentrating the radiation?
By a factor of 10 or more. So the fly ash, the stuff that's caught in the chimneys, can be significantly radioactive. Living near an unshielded coal ash dump can, in theory, expose you to more radiation than living near a properly shielded nuclear power plant.
Wow, that really flips the script on how we perceive risk. And then, of course, there's the environment.
Climate change is the big one. Coal is the single largest contributor to the growth in global CO2 emissions. It's just so carbon heavy. It releases more CO2 per unit of energy than oil or natural gas.
And the targets are brutal. I mean, if we want to meet the Paris Agreement goals keeping warming below 2 degrees Celsius, we essentially need to have coal use between 2020 and 2030.
Have it. In a decade. While China and India are still building plans to support their developing economies, that is a monumental challenge.
But there's another environmental impact that's even stranger, more cinematic, the forever fires.
The coal seam fires.
Have you ever heard of the Brennenderberg?
The burning mountain in Germany, yes.
It's a coal seam fire, but here's the wild part. It has been burning since 1668.
Wait, 1668, like Isaac Newton times.
Yes, continuously. And these underground coal fires are a global phenomenon. You have them in the U.S. Centralia. Pennsylvania is the famous one that inspired the Silent Hill games.
Right.
You have them in China and India. How does a rock underground stay on fire for over 300 years?
It just smolders. A coal seam catches fire, maybe from lightning, a forest fire, or often human error. Because it's underground, oxygen just seeps in slowly through cracks in the soil. It doesn't roar like a bonfire, it creeps. It just eats the coal seam inch by inch.
That sounds terrifying. The ground is literally burning beneath your feet.
And they are incredibly hard to put out. You can't just spray water on them. The heat is so intense, the water just turns to steam instantly. They release massive amounts of CO2, mercury, toxic fumes.
So we have a fuel that kills us when we burn it on purpose and also burns itself underground for centuries. It really feels like we are dealing with something primal and dangerous here.
Which is why the whole conversation has shifted to mitigation. You know, if we can't quit cold turkey because of steel, because of the developing world's energy needs, can we make it cleaner?
Clean coal. We hear that term in political ads all the time. Is it? Is it real?
Well, you have to look at what they mean by clean. The definition has shifted over time. Originally, back in the 80s and 90s, clean coal meant scrubbing out the sulfur dioxide and nitrogen oxides.
The chemicals that cause acid rain.
Exactly. And we actually did a pretty good job with that. I remember learning about acid rain in school, but it's not the headline news it used to be.
That's true.
Regulations force power plants to install scrubbers, basically, these showers in the smokestacks that use limestone to trap the sulfur. It worked. Acid rain in the West has dropped significantly. So in that specific sense, coal did get cleaner.
But today, when politicians say clean coal, they aren't talking about acid rain, they're talking about CO2.
Right. Today it implies carbon capture and storage, or CCS.
Yeah.
This is the idea that you can capture the CO2 before it leaves the chimney.
How does that actually work? Do you just put a bag over the chimney?
It's chemical engineering. You bubble the exhaust gas through a solvent, usually a chemical called an amine, that acts like a magnet for CO2. It just grabs the carbon.
Yep.
Then you take that solvent, you heat it up to release the CO2 as a pure gas, you compress it into a liquid, and you pump it deep underground.
So you're basically putting the carbon back where we found it.
The physics works. We can do it. The problem is the economics. It is a nightmare.
Why?
Because it's incredibly expensive to build these facilities, and it lowers the efficiency of the power plant. You have to use a lot of energy, they call it the parasitic load, just to run the capture equipment. You might use 20% of your electricity just to catch the emissions.
So you're burning more coal to get the same amount of power just to catch the smoke.
And unless there's a massive tax on carbon, it is always cheaper to just dump the CO2 into the air for free.
Yeah.
That's why, as of 2024, only a handful of plants worldwide are using CCS effectively at scale. It's currently more of a hope than a widespread reality.
And this leads to some tricky language in international agreements. I saw the terms abated versus unabated coal.
This is the loophole.
Yeah.
If a country promises to phase out unabated coal, they are saying we will stop using coal plants that don't have carbon capture.
But since almost no plants have carbon capture.
It leaves the door open. They can say, we are building this new plant, and it will be abated eventually. Or they can count a plant that captures only a tiny fraction of its emissions as abated.
So abated is the magical future coal that doesn't ruin the climate, but unabated is the dirty reality we have now.
Precisely. And the danger is relying on a technology that hasn't scaled yet to save us from a physics problem that is happening right now.
So where does that leave us? I mean, we've looked at the geology, the giant bugs, the lignin lag. We've looked at the history from Romans to the Industrial Revolution. We've seen the economics of stranded assets and the horror of the health impacts.
It really feels like a turning point.
It feels like coal is this incredible double-edged sword that built civilization and now threatens to tear it down.
I think that's a fair assessment. Coal is a concentrated battery of ancient life. It allowed us to break through the energy ceiling of the 18th century. It gave us the modern world. It gave us steel, fast travel, light in our homes.
But the bill has come due.
It has. It's like we took out a high-interest loan from the Carboniferous period, and the collectors are knocking at the door.
And the question is whether we can pay it off. The transition is happening. I mean, the UK, the birthplace of the coal revolution, closed its last deep mine in 2015. They just shut down their last coal power station.
The economics of renewables are winning.
Yeah.
But the sheer inertia of the coal infrastructure, especially in Asia and in the steel industry, is massive. It's a very heavy ship to turn.
It really makes you think about how we define eras. You know, we talk about the Stone Age or the Bronze Age as these ancient things. But looking at the data, looking at the smoke in the air, are we still in the coal age?
We might just be living in the tail end of it. The coal age has lasted a few hundred years, a blink of an eye in geological time, but an eternity for the atmosphere.
And here's the thought to leave you with. Final provocation.
Go for it.
Coal is fossilized sunlight. It's energy from the sun that hit the Earth 300 million years ago, was captured by a tree, buried, and saved for us. We are literally burning the past.
While right outside, the sun is shining today.
Exactly. The sun delivers more energy to the Earth in a single hour than humanity uses in an entire year. And the race now is whether we can switch to using current sunlight solar power fast enough before the smoke from the past chokes the future.
It's a race between the sun that shone on the giant dragonflies and the sun that's shining on us right now.
And the winner of that race will determine the climate for the next few thousand years.
No pressure.
No pressure at all. Just the fate of the biosphere.
A fascinating deep dive into a humble black rock.
Thanks for exploring it with us.
Thank you.
And thank you for listening. We'll catch you on the next deep dive. Welcome back to the Deep Dive. We are back with another stack of research, and today is going to be a little bit different. Usually we're looking at something cutting edge, or maybe a geopolitical shift, or, some new tech trend. But today we are looking backward.
Way backward.
We are engaging in a bit of time travel today.
We really are.
And we are looking at a system, a piece of technology, really, that you probably see every single day of your life, but you almost certainly take it for granted.
Oh, for sure.
I want to start with a visual just to sort of set the scene.
Go for it.
Okay. Picture the year we're in right now, the current year.
Okay, got it.
If you see it written on your phone or on a calendar or, I don't know, in a spreadsheet, it's just data. It's 4 digits.
Right.
2026.
Functional.
It's functional. It tells you where you are in the timeline.
Right.
But if I ask you to picture that same year carved into the cornerstone of a massive bank building, or maybe flashing on the screen at the very end of some moody film noir.
Then it transforms. It becomes MMX6.
MMX66, and suddenly it feels different, doesn't it?
Oh, completely.
It doesn't just feel like a date anymore. It feels
heavy.
Heavy, exactly.
Yeah.
It feels permanent. It feels like it has weight to it.
It really does.
We're talking, of course, about Roman numerals. And I have to admit, when I first looked at the packet for this deep dive, my first reaction was, okay, cool, but is there really an hour of conversation here?
Laughs.
Yeah. I mean, I learned this in third grade. I is 1, V is 5, X is 10, done.
That's the standard reaction. We all think we know it because we learned the code.
Right. But looking through the research, specifically this huge historical overview we've pulled from the archives, the story of these numbers is just so much weirder.
Yes.
It's so much messier and, frankly, so much more chaotic than I ever realized.
It really is. It's one of those topics where the school version we all learned, the neat little chart on the chalkboard, is basically a myth.
A myth.
Or if not a myth, it's a kind of polite fiction. It's a modern cleanup operation of a system that was historically anarchic.
Anarchic is a strong word for numbers.
But it fits. I mean, we tend to think of the Romans as these rigid, disciplined engineers.
Straight roads, square legions, strict laws.
Exactly. So we assume their numbers must have been just as rigid. But the reality is the way they used numbers was incredibly flexible.
So our mission today is to strip away that third grade myth.
Let's do it.
We're going to look past the Super Bowl logos and the movie copyright dates and really try to understand the machinery. We're going to find out why the Romans essentially ignored their own rules.
Mm-hmm.
Discover a secret system of fractions based on the number 12, which, spoiler alert, is why we have the word inch.
That's a great little detail.
And figure out how on earth you build an empire without a zero.
That zero question is the one that really trips everyone up. It's like the cognitive gap between us and them.
It is. So let's dive in. I want to start with the rules versus reality, because this is where the biggest shock was for me.
Okay, let's do it.
Let's go back to that classroom. If I walked into a third grade class today, or even just grabbed a random person on the street and asked them to write the number 4 in Roman numerals, what do they do?
Oh, they would almost certainly write IV.
Eh.
An I followed by a V.
And if you ask them why, they'd recite the rule we all know, right?
Subtractive notation.
Subtractive notation.
Right. The logic is simple. You can't have 4 I's in a row because it looks clunky. It takes up too much space.
So the rule says you place the smaller value before the larger value to indicate subtraction. 5 minus 1 equals 4.
It's elegant. It's clever.
It is. And it's the standard we use today. If you look at a textbook or a standard conversion chart on Google, that is the rule. But here's the first big shock from the historical record.
Yeah.
The Romans almost never did that.
Rarely. They just didn't.
They didn't use RV.
Very rarely. I mean, for the vast majority of Roman history, and certainly for the casual user, the shopkeeper, the soldier, the stonemason, the number 4 was the third.
Just 4 lines?
4 vertical strokes?
Yeah. So the strict rule against 4 identical symbols in a row, it just didn't exist.
It's largely a modern stylistic preference that got kind of, retroactively applied as a law.
Huh.
Think about it from the perspective of someone living in 100 AD. You aren't a mathematician. You're counting bushels of wheat. 1, 2, 3, 4. It is cognitively much easier to just make 4 marks than to perform a sudden subtraction operation in your head.
That makes a lot of sense. Subtraction requires foresight. You have to look at the V, realize there's an I before it, and then calculate.
Right.
But 4 lines is just 4 lines. It's a tally.
Exactly. It's visual versus abstract. And we have hard evidence of this carved in stone. We aren't just guessing.
Okay, where?
The most famous example is the Colosseum, the Flavian Amphitheater.
Right. So help me visualize this. We're in Rome, 1st century AD. The Colosseum has just opened.
It's this massive structure. It holds, 50,000 to 80,000 people. It's the Superdome of antiquity. Now, just imagine the chaos of getting 50,000 people into their seats.
It's hard enough getting into a concert today with a QR code.
Exactly. So to manage the crowd, the Romans had a system. They had 80 entrance arches on the ground level.
Okay.
And each arch was numbered so the spectators could match their ticket, which was a pottery shard to the gate.
Just like finding section 101, gate A.
Precisely.
Yeah.
So if you go to Rome today, you can still walk up to the Colosseum and see these numerals carved above the arches. They're weathered, but they're legible. Gate 23 is marked XA3.
Standard stuff.
Gate 52 is IL4. But if you walk around the perimeter to gate 44...
Edge, according to the school rules, should be XLV, XL plus 4.
You'd expect that. But on the stone, clearly carved by a Roman artisan, it says XL3.
No way. So they mixed the systems.
Yep.
They use a subtractive method for the 40, the XL, but they use the additive method, the 4 I's, for the 4.
They did. And that tells us something really profound about how they viewed these numbers. They weren't following some rigid syntax like computer code where a syntax error crashes the program.
Right.
They were using whatever was clearest to read at that magnitude.
It's just pragmatic. XXVI leaves no room for doubt.
Right. And this preference for the four eyes actually survived the fall of Rome. It survived for thousands of years. We see it everywhere today, but most people never notice it.
You're talking about clocks.
I am. Have you ever really, scrutinized a grandfather clock? Or even a nice wristwatch with Roman numerals?
You know, I check the time, but I don't think I've ever audited the typography.
Well, next time you see a traditional clock face, look at the 4 o'clock position. It is almost universally 4-3.
Really?
It is very, very rare to see a phi on a clock face.
What about Big Ben?
Big Ben is actually the exception. That's the one people point to. Big Ben uses the 4th. But most other famous clocks use the 3.
But why? If we know 4 is the correct number 4, why do clockmakers insist on the 4 lines?
It comes down to aesthetics. It's all about visual balance.
Oh, so?
Okay, picture the circle of the clock face. You have 12 numbers arranged in a circle.
Yeah.
If you use third for 4 o'clock, look at what happens to the symmetry. You end up with these 3 distinct groups of 4 numbers.
Okay, break that down for me.
So the first 4 numbers are 1, 2, 3, 4. If you use 3, then all 4 of those numbers use only the symbol I.
I, there, 3, 3. Okay, I see that. It's the I quadrant.
Exactly. Then the next 4 numbers, 5, 6, 7, 8, they all involve the V symbol. V, 6, 7, 8. That's the V quadrant.
And the final 4, 9, 10, 11, 12 all involve the X.
Right. 9, X, LF, 12. It creates this beautiful radial symmetry. 3 groups of 4.
That is surprisingly satisfying. I've never thought of that.
It gets better. Visually, 3 is a heavy number. It has 4 strokes. It's wide.
Okay.
On the opposite side of the clock face is the number 8, 8. That is also a heavy, wide number, 4 characters.
So 3 balances 8.
Correct. If you use 4, it's a skinny number, 2 characters. It would look lopsided across from the big, heavy 8. The clock would look like it was tilting to the left.
That is amazing. It's typography winning over mathematics.
Typography winning over mathematics is actually a great summary of Roman numerals in general.
Wow.
They are graphic symbols first and mathematical tools second.
But the chaos goes deeper than just the number 4, doesn't it?
Oh, yeah.
In the research, there was this part about the IRX notation that absolutely broke my brain.
Ah, yes. The 18th Legion.
This sounds like a sci-fi movie, the 18th Legion.
It was a very real, very famous Roman military unit. Now, if you or I were to write 18 in Roman numerals, we'd write 8th.
10, 5, 3 ones. Simple addition.
Right. But we have historical records, monuments, and markers left by the Legion themselves, where they identified their unit as the IRX.
So IX.
Which reads as 2 subtracted from 10, or I guess more accurately in the full context, 2 subtracted from 20.
Wait. I thought the rule, even if we ignore the third thing, I thought the rule was you could only subtract 1 digit. You can do IX for 9, but you can't do IX for 8.
In the standardized modern version, you absolutely cannot. If you did that on a math test, you'd fail. But the Romans didn't care about our tests.
So what did they care about?
They cared about their language.
It's linguistic.
It's entirely linguistic. The Romans spoke Latin. And in Latin, the word for 18 is duodevigenti.
Okay, let's parse that.
Duo means 2. D means from. Vigenti is 20. The word literally means 2 from 20.
Oh, so when they wrote IIXX, or shorthand IIX, they were just transcribing the way they spoke. 2 before 20.
Exactly. It's like if we wrote the number 19, not as a 1 and a 9, but as 120, they were writing the words using the symbols.
That is fascinating. It explains why the rules felt so fluid. They weren't checking a rule book, they were just writing down what they said.
We see the same thing with the number 98. Sometimes they wrote it as Ikai.
2 from 100.
Yes. Instead of the standard XXVI, 90 plus 8, they just said it's 2 away from 100, I. Much easier.
It makes the system feel so much more human. It wasn't an abstract code. It was shorthand for speech.
It was a living system. And because it was living, it mutated. It wasn't static. Even into the 20th century, we see architects and designers ignoring the rules for aesthetic reasons.
You mentioned the Admiralty Arch in London in the notes. That's a fairly modern building, relatively speaking, 1910.
1910. Now, how do you write 1910 in standard numerals?
Okay. M for 1,000, CM for 900, X for 10, MCMX.
Short, punchy,
Huh.
4 characters.
Right.
But if you look at the Admiralty Arch, inscribed in massive letters across the top, it says MDCCCCX.
MD and then 4 Cs.
4 Cs, 4,500 plus 4 100s. Again, avoiding the subtractive CM form.
But why? Just to make it longer.
And yeah, the prevailing theory is exactly that. The architect wanted the inscription to be wider. He had a big arch to fill. MCMX is too short. It looks dinky.
Lofts.
MDCCCX takes up more physical space on the stone. It looks grander. It matches the scale of the building.
So you can just stretch the number to fit the architecture?
Apparently so. If you have a chisel and a hammer, you make the rules.
That's a powerful position to be in. But sometimes these variations aren't aesthetic choices. Sometimes they're just straight up mistakes.
Oh, yeah.
And the research had this incredible story about a movie copyright.
Oh, this is a classic. The movie is The Last Time I Saw Paris.
MGM movie, 1954, Elizabeth Taylor.
Great film. Now, at the end of every movie, you see the copyright notice. It's usually the very last thing on the reel.
Right, Roman numerals.
And 1954 should be written as MCMLIV. M for 1,000, CM for 900, L for 50, IV for 4.
Okay.
But the title artist, the person painting that card, messed up. They wrote MCMXLIV.
Let me decode that. MCMXLV, that's 1944.
Exactly. They accidentally wrote 40
Yeah.
XL instead of 50. They dated the movie 10 years before it was actually made.
Does that really matter? I mean, everyone knows when the movie came out. It's in the newspapers.
It matters for copyright law. Especially back then, U.S. copyright terms were strictly based on the date in the notice.
Oh, no.
By printing an earlier date, they theoretically shortened their copyright term by 10 years.
That is a very expensive typo.
It is. And there was a genuine legal question. Did the error invalidate the copyright entirely? Because the notice was defective.
That is wild. A typo in a dead numbering system could cost you the rights to your movie.
Fortunately, the courts usually rule that if it's an honest mistake and doesn't harm anyone, you don't lose the rights. But it highlights the danger of using a prestige system that nobody really speaks fluently anymore.
It's like getting a tattoo in a language you don't speak. You might end up with soup written on your arm instead of strength.
Exactly. It's a risky aesthetic.
I want to pivot a bit. We've talked about how the numbers are used or misused and the flexibility of the rules, but I want to go back to the very beginning.
Okay.
Where did these symbols even come from?
The origin story.
Because the story I always had in my head is that they're letters. M is for mil, 1,000. C is for centum, 100. So I just assumed the whole system was an abbreviation of Latin words.
That is the common belief. And it makes perfect sense, which is usually a sign in history that it's wrong.
Lasses, of course. Nothing is ever that simple.
The M and C connection is actually a happy accident or a convergence that happened much later. The true origin of Roman numerals isn't the alphabet at all.
Then what is it?
It's tally marks.
Tally marks, like scratches on a prison wall.
Or notches on a shepherd's stick.
Yeah.
Imagine you're an Etruscan shepherd in Italy, maybe 500 BC, before Rome is really Rome.
Okay.
You're out in the field counting your sheep.
I'm in the field. I have a stick and a knife.
Sheep 1 comes by. You cut a vertical notch.
Yeah.
I, sheep 2, notch 2, sheep 3, notch 3.
Simple.
But when you get to, say, 8 or 9, counting those little identical lines becomes a nightmare. Your eye glazes over. You can't tell at a glance if it's 8 or 9. You need a way to group them, a checkpoint.
Like how we use the diagonal slash when we do tally marks on paper today.
Yeah.
We do 4 lines and then cross them out to make a bundle of 5.
Exactly. That is a universal human impulse. So the theory is on the 5th notch, the shepherds didn't just cut a line. They made a double cut to distinguish it. If you cut 2 lines meeting at an angle, what shape do you get? A V. So the V isn't the letter V. It's a graphic representation of a check mark or a notch on a tally stick.
That is so much more intuitive than V is an arbitrary letter.
And then you keep going, 6, 7, 8, 9, and you hit 10. You need another checkpoint. So you do 2 Vs, one upright and one upside down, meeting at the points.
Which makes an X.
Precisely. So I, V, and X are essentially pictures of cuts in wood. There is another theory that relates it to hand signals. Holding up 5 fingers makes a V shape with the thumb and forefinger, but the tally stick theory is very robust archaeologically.
Okay, so that explains the small numbers. But what about the big ones? L, C, M. Surely M is mil.
This is where it morphs from tally marks to paleography, the study of old handwriting. Let's take the symbol for 50. Originally, it wasn't an L. It was a symbol that looked like an arrow pointing down or an inverted T.
Okay, I'm trying to picture that.
But over centuries, scribes writing quickly on wax tablets or papyrus started to curve the line. The bottom stroke flattened, the right side curved up, and started to look like an L.
So it just drifted into the letter L because of lazy handwriting?
Efficient handwriting.
Yeah.
And the M is the best story.
Tell me about the M.
Originally, the Etruscan or early Roman symbol for 1,000 was a circle with a cross inside it, or sometimes a circle with a vertical line through it. Imagine the Greek letter phi.
Okay. A circle with a line.
That symbol is hard to write quickly. It's like lift your pen, draw a circle, draw a line. So people got lazy.
Blast.
They stopped closing the circle. It became two curved humps, like a sideways figure 8 or an infinity symbol.
Which looks a bit like a curvy M.
Right. And here's the kicker. Because the Latin word for 1,000 happened to be mil, the Romans saw this curvy symbol evolving and said, hey, that looks like an M. And M stands for mil. Let's just use M.
So it's a back formation. They rationalized the symbol after the fact.
Exactly. It's evolution, not intelligent design. They fit the symbol to the word later on.
It's amazing to think of this system evolving from shepherds cutting sticks in a field to being carved into marble monuments. It feels so organic.
It is. It's a very human system. It relates to hands, tallies, spoken language, which explains why it lacks some things that we consider essential in math today.
Which brings us to the biggest missing piece, the elephant in the room.
Is zero.
How do you build an empire, engineer aqueducts, and conquer the known world without a zero?
It's a great question. And the answer lies in the difference between a positional system and a non-positional system.
Break that down for us.
So in our modern Arabic numerals, the position of a digit tells you its value. In number 2026, the 0 is doing heavy lifting. It's a placeholder telling you there are no hundreds.
Right.
If you take that 0 away, you have 226. The number collapses.
The 0 holds the structure. It keeps the 2 in the thousands column.
Exactly. But Roman numerals are non-positional. The symbol X always means 10 no matter where it sits. You don't need a placeholder to tell you there are no hundreds because you just don't write any hundreds.
You just skip it.
You just skip it. If you have 2026, you write MM 2000s XX 20 VI 6. You don't need to say N0 hundreds. The symbols carry their own value independent of a column.
So they didn't have a symbol for 0 because they didn't need it for writing numbers.
Right.
But did they understand the concept of nothing?
Philosophically, yes. They had the word nulla, meaning none.
Right.
And interestingly, medieval monks, who were the main users of Roman numerals for 1,000 years, sometimes used the letter N for nulla to signify 0 in tables.
Like a shorthand.
Yes. But it wasn't a number you calculated with. You couldn't do 5 times 0 equals 0. That math wasn't part of the numeral system.
This brings up a massive practical question. If they didn't have 0 and the numbers are just letters, how do they do math?
This is the key. They didn't do math with the numerals.
What do you mean?
Try to multiply x8 using just the letters. Try to act it out in your head.
XL times X, L times V. It's a mess. I can't do it.
It's practically impossible. The numerals were not designed for calculation. They were designed for recording.
So how did they calculate the budget of the empire?
They used an abacus, or a counting board.
Explain the setup.
They had a board with grooves in it. One groove for ones, one for tens, one for hundreds. And they had little pebbles. In Latin, the word for pebble is calculus.
Hence, calculus. Calculate.
Exactly. To calculate literally means to move pebbles around. So you would do the math physically moving beads or stones in columns. When you were done, you'd look at the board, see the result, and then write it down using Roman numerals.
So the numerals are just the receipt. They aren't the calculator.
Perfect analogy. The numerals are the save file. The abacus is the processor.
That explains so much. But the abacus brings me to the next big surprise in the research. Fractions.
Yes. The lost world of Roman fractions.
We assume Roman numerals are integers only, 1, 2, 10. But you can't run an economy on whole numbers. If I'm selling grain, I need to sell half a bushel.
Right.
If I'm taxing land, I need to tax 1/3 of an acre.
And this is where the Roman system is arguably better, or at least more practical, than our metric system for physical trade.
Better. That's a bold claim. We love our decimals.
We do. We use a base 10 system. It's great because we have 10 fingers. But mathematically, 10 is a bit annoying.
How so?
It's only cleanly divisible by 2 and 5.
Yes.
That's it. If you try to divide 10 by 3, you get 3.3333, an infinite mess. If you divide by 4, you get 2.5, also messy.
Okay.
Now look at the Roman system. They used a base 12 system for their fractions, a duodecimal system.
Why 12?
Think about the factors. You can divide 12 by 2, 3, 4, and 6 cleanly, no remainders. If you are a pizza shop, You can slice a 12-slice pizza for 2 people, 3 people, 4 people, or 6 people, and everyone gets the same amount.
That is incredibly versatile for trade.
It is. So their main unit of fraction was called the uncia, and an uncia was 112th of the whole.
Uncia, that sounds familiar.
It should. It's the etymological root of the English words ounce and inch.
No way.
Yes way. An inch is 112th of a foot. An ounce is historically 112th of a pound. It all comes from the Roman uncia.
Wow.
We are still using Roman math every time we use a ruler.
That is a direct line from ancient Rome to the ruler sitting on my desk right now. That is wild.
Like it connects us directly. So in Roman notation, a single dot was 112, 2 dots was 212, or a sixth, 3 dots was 312, a quarter, and they had names for all of these.
So if I wanted to write 512,
You would write 5 dots, and often they would arrange these 5 dots in a specific pattern. Imagine the face of a die. A dot in each corner and one in the middle.
the classic number 5 on dice.
That pattern and the value 512 is called a quincunx.
Quincunx. I've heard the word quincunx used in literature or design, but I never knew as a fraction.
It's a beautiful word. And the Romans had symbols for all combinations. They also had a symbol for half,
Which was?
the letter S. S stood for semis, which means half. So if you saw V's, that would be 7.5.
Okay, that's simple enough. What about smaller fractions? Say 7.5 plus another 12.
You would write VIIS, followed by a dot. S dot, that's 712ths. 6 twelfths plus 1 12th.
It seems complicated to learn, but once you know it, it's actually very precise for physical goods.
It's extremely practical for a non-digital world. You're measuring weight, length, volume. Base 12 is superior in that context.
So we have fractions, we have the zero issue resolved, but what about going big? I mean, really big. The standard chart ends at M for 1,000. If you write MMMCMXCIX, you're at 3,999.
Right.
That's the ceiling of the school numerals. How do they count the budget of the empire or the number of soldiers in a massive campaign? They must have had numbers bigger than 4,000.
They absolutely did. And this is where the system starts to look like secret code or ASCII art. They developed extensions to the notation to handle scaling up.
Walk us through the apostrophist method. That sounds complicated.
This goes back to that curved symbol for 1,000 I mentioned earlier, the CI followed by a backward C. It looks like a C, an I, and then a C that's been flipped backwards. Kind of like parentheses, I.
Okay, so brackets around an I.
Right, that meant 1,000. If you wanted 10,000, you added another layer of brackets.
Yeah.
So like CCI followed by 2 reverse Cs.
It's almost like wrapping the number in more and more layers to multiply it.
Exactly. It's a bit complex to visualize, but essentially they use these curved bracket shapes to denote powers of 10.
It feels very programming-ish, like nested functions.
It is. But there was a simpler method that became popular later called the vinculum.
The vinculum sounds like a Harry Potter spell.
It does. Vinculum basically means bond or tie in Latin. In math, it refers to a horizontal line drawn over a number.
An overbar.
Yes. If you take a standard Roman numeral, say V5, and you draw a line over the top of it, it multiplies the value by 1,000.
So V with a bar is 5,000.
Correct. X with a bar is 10,000. M with a bar would be a million.
That is so much easier than writing M 1,000 times.
Much easier.
Yeah.
And if you really needed to go massive like hundreds of thousands, they sometimes used a 3-sided box. A line over the top and lines down the sides. That can multiply by 100,000.
So they had the tools. They weren't limited to 3,999. That's just a limitation of the standard chart we teach kids.
Exactly. The system was expandable. It just wasn't standardized. Different scribes used different methods. Some used the brackets, some used the bars. It was a bit of a free-for-all.
Which brings us to the inevitable question. If the system was chaotic, lacked a true zero, and had competing methods for big numbers, why did it last so long? And why is it still here?
The survival of Roman numerals is a story of cultural inertia and prestige. When Arabic numerals, the 0 through 9 we use today, arrived in Europe around the 11th century, they didn't just take over immediately.
I assume because they came from the Islamic world via Al-Andalus in Spain, there might have been some cultural resistance.
There was definitely that, but also bookkeepers and accountants were suspicious of them.
Suspicious of the numbers.
Think about fraud. If I owe you money and I write a promissory note, in Arabic numerals, if I write 100, it is very easy for you to add a 0 to the end and make it 1,000.
True. Or change a 1 to a 7.
Or change a 0 to a 6 or a 9 with a stroke of a pen. But Roman numerals, they're structural. CMV. They are harder to alter without it looking obvious.
Oh, interesting. So Roman numerals were seen as more secure.
Harder to forge. In fact, in medical prescriptions, doctors used Roman numerals well into the 20th century. And they had a specific trick. If they wanted to write 3, they wouldn't write 3, they would write T.
AJ at the end.
Yes. A terminal J with a tail. That prevented anyone from adding another I to the end to up the dosage.
That is a fantastic detail. The trailing J as a security feature.
Right. So for legal and financial documents, Roman numerals held on because they felt permanent and secure. But eventually the math won.
Right?
You can't do calculus with Roman numerals.
No, but they didn't disappear. They just migrated. They moved from being a tool of calculation to a tool of what?
Decoration?
Decoration, gravitas, and hierarchy. That's their modern niche.
Let's talk about gravitas. We use them for kings and queens. Queen Elizabeth II, Pope Benedict XVI. Right. Regnal numbers. It implies a lineage. It links the current leader back to ancient history. Elizabeth II, with an Arabic 2, looks like a sequel to a movie.
Yeah. Wow, that's...
Elizabeth II looks like an institution.
It does. It looks serious. Same with cornerstones on buildings, built in MMXX. It feels like it's meant to stand for 1,000 years.
That's the cultural gravity of the numerals.
Right.
They signal to the viewer, this is important, this is history.
And then there's the Super Bowl.
The Super Bowl is the ultimate modern example of this. The NFL uses Roman numerals to make the game feel epic, gladiatorial.
Except for that one year.
Super Bowl 50.
The year the system broke.
The year aesthetics won over tradition. Super Bowl L. Just the letter L.
L is universal slang for loser now. You can't have the Super Bowl loser.
Exactly. It looked weird. It wasn't symmetrical. So for that one year, the NFL switched to Eric 50, and then immediately went back to LI 51 the next year. It proves that we use these numerals primarily for how they look, not just what they count.
We also see them in science, which surprised me.
Yes. Chemistry. Oxidation states, iron 2 versus iron 3. It distinguishes the charge of the atom. It's a very specific technical use, but it's standard. And the periodic table group numbers used to be Roman, though that's changing.
In music theory.
Oh, huge in music. Chord analysis, the I chord, the 4 chord, the V chord. Every musician knows what a IVV progression is. Writing 1, 4, 5 just doesn't look the same on a sheet of analysis.
So it distinguishes function.
Exactly. It distinguishes the function of the chord from the specific note numbers.
It's amazing how deeply embedded it is. We talked about clocks earlier, but even graph quadrants, quadrant 4, 2, 3, 4.
It's a way of separating meta information from data. If your data is in Arabic numerals coordinates, values, you label the structure of the quadrants in Roman numerals to avoid confusion.
That's a great way to put it. Roman numerals have become the labels of our world, while Arabic numerals are the content.
That's a perfect distinction.
So as we wrap up this deep dive, I'm left with a totally different appreciation for MMXX. It's not just a pretension, it's a survivor.
It is. It's a survivor from a time when numbers were physical fingers, notches, pebbles. It's a system that refused to die because it adapted. It bent the rules. It integrated with language.
And it's still breaking rules today.
It is.
I want to leave our listeners with a challenge. The next time you see a Roman numeral, whether it's on a clock, a copyright date at the end of a movie credits, or a chapter in a book, look closer.
Check the 4. Is it 4 or the 3? Check the date. Does it follow the subtractive rules, or is it doing its own thing?
And remember that for every nice, neat M or C you see, there's a history of shepherds, soldiers, and rebels who decided that sometimes writing IX just made more sense.
The map is not the territory, and the rule book is not the history.
Exactly. Thanks for diving in with us. We'll see you in the next one.
MMX7.
Maybe. Catch you then. Hello, everyone, and welcome back to the Deep Dive.
Hello.
Today, we're doing something a little bit different. Usually, we take a topic you might not know much about, right? Some obscure historical event or a complex piece of new tech, and we unpack it for you.
Right.
But today, we are tackling something that every single person listening has lived through. We're taking a huge step back to look at the event that defined the early 2020s.
It is, it's arguably the most significant global event of the 21st century so far. And while we all have our personal memories of it,
Oh, we definitely do.
the difference now, a few years on, is that we actually have the data.
Yeah.
We can understand what really happened.
We are talking, of course, about the COVID-19 pandemic, and I know what you're thinking. We all went through it. We remembered the masks, the Zoom happy hours that got awkward after about 20 minutes.
The sourdough starters.
The sourdough starters that we inevitably killed, yes. But here we are. It's February 6, 2026. The dust has settled, and we have this massive stack of encyclopedic records, epidemiological data, economic reports that lets us look at the whole picture in a way we just couldn't when we were in the middle of it.
Exactly. There's a concept historians use called the fog of war.
Right.
When you're in the middle of the battle, you can't see the map. You just see the mud right in front of your face.
For the last, 6 years we've been in that fog?
We have. But now the fog is lifted just enough that we can see the anatomy of the pandemic. We can see how it started, how it mutated, and how it fundamentally reshaped society, economics, and even our biology.
And just to set the stakes here, because I think we can get desensitized to the numbers after seeing them on news tickers for years and years.
Absolutely.
As of today, February 6, 2026, the official death toll stands at over 7.1 million people. That's the number on the dashboard.
It is. But that's where the retrospective data gets.
Yeah.
Well, it gets really difficult and, frankly, quite sobering. That 7.1 million is just the confirmed count. It's the people who got a test, got a diagnosis, and their death was officially recorded as being from COVID-19.
Okay, so what's the real number?
When you look at the estimates of the true toll, and this means factoring in excess mortality.
People who died but weren't tested, or maybe died because the hospitals were full.
Exactly, all of that. When you factor that in, the estimates range significantly higher. We're looking at somewhere between 18.2 million on the low end and 33.5 million deaths on the high end.
33.5 million. That's hard to even wrap your head around.
That's staggering.
It's the population of a large country, just gone.
It puts COVID-19 as the 5th deadliest pandemic or epidemic in all of recorded history.
Wow.
It sits there in the history books alongside the plague of Justinian and the 1918 flu.
Right.
This wasn't just a bad flu season, it was a historical pivot point for the human species.
So our mission today is to move past that daily news cycle that we all doom scroll through.
Well,
we want to understand the mechanics of this thing. We have records covering epidemiology, virology, economics. We're going to unpack all of it. We need to understand the biology of the virus, the psychology of our response, and the sociology of the aftermath.
we need to strip it down to the studs.
Let's start at the very beginning, or at least what we thought was the beginning. Section 1, origins and the name game.
Right.
Now, the story we were all told, the official start, was December 2019 in Wuhan, China. A cluster of pneumonia cases with an unknown cause.
That's right. On December 31st, 2019, the WHO, the World Health Organization, was formally notified about this cluster. That's the date that's etched in the timeline. It's when the bureaucratic clock started ticking.
But like with most things in science, when you look closer, the biological clock had actually started ticking much, much earlier.
A lot earlier.
Right, because we have this concept of the official start versus the likely start. How do we even know it started earlier? It's not like we have a time machine.
In a way, we kind of do. We have something called molecular clock analysis.
Okay, you have to unpack that for us. It sounds like something straight out of a sci-fi movie.
It's actually pretty standard evolutionary biology. Viruses, you see, they mutate at a relatively constant rate.
Okay.
So think of it like a ticking clock. Every time the virus replicates and jumps from one person to the next, there's a chance for a little genetic typo, a mutation.
Right.
By looking at the genetics of the virus samples from, say, January 2020, and comparing them to samples from June 2020, scientists can rewind that clock. They can calculate how long it would have taken for those specific mutations to accumulate.
So you're basically tracing the family tree of the virus back to the great-grandfather virus.
Precisely. And when you run that analysis on SARS-CoV-2, it suggests that human-to-human transmission likely started as early as October or November of 2019.
October, November. So it was circulating for months before the alarm was really sounded.
It's very possible. The virus was likely ghosting through the population, being mistaken for a bad cold or a nasty flu.
And we have other evidence for this, right? It's not just the genetic modeling.
Correct. We have retrospective testing that supports this idea. Researchers went back and tested old samples from patients in France.
Old samples.
Yeah, samples taken from people who were hospitalized with pneumonia before we even knew what COVID-19 was. They went back to the freezers. And they found a confirmed case dating all the way back to December 27, 2019.
Wait, in France? In December?
In a Parisian suburb, yes.
That really changes the narrative of containment, doesn't it? I mean, I remember watching the news in January 2020, seeing the lockdown in Wuhan, and thinking, well, it's over there. If they just lock down the city, we'll be fine.
And that was the fatal flaw in our collective thinking. By the time we were watching that lockdown on TV, The virus had likely already boarded several international flights. It was already in Europe.
And in the U.S. too, right?
Yes, there was also a death in the United States on February 6, 2020, which at the time was much earlier than the initial timeline suggested. The virus was just moving so much faster than our ability to detect it.
So by the time we saw the smoke, the fire was already out of control.
By the time we saw the fire, the sparks had already landed in dry grass all over the world.
And speaking of seeing the fire, we have to talk about the people who tried to sound the alarm early on, the whistleblowers.
Yes, this is a really tragic part of the early timeline. In early January, before the official public pivot from the authorities, there were doctors in Wuhan seeing this pneumonia of unknown cause.
Right.
They were looking at CT scans of lungs that looked suspiciously like SARS from 2003. One of the most famous of these doctors was Dr. Li Wenliang.
I remember his name. He wasn't even an infectious disease expert, was he? He was an eye doctor?
An ophthalmologist, correct. But he saw the reports from his colleagues, and he posted in a private chat group with his medical school alumni.
What did he say?
It was basically a warning. He said, wear protective gear, there's a SARS-like virus spreading. Just a heads up to his friends.
And the response from the local authorities was not great.
Not to investigate, but to silence.
Yeah.
Exactly. He and 7 other doctors were detained by the police. They were forced to sign these statements admitting to spreading false rumors and severely disturbing social order.
False rumors. That is just chilling in retrospect.
It really highlights that fundamental tension between public health and information control. And the story gets worse.
He contracted the virus himself.
He did. He contracted it from a patient and tragically passed away in February 2020. His death sparked this massive outpouring of grief and anger, not just in China, but globally. It became this symbol, a wake-up call, that the systems that were meant to protect us were in fact failing.
It really set the tone for all the confusion that followed. And speaking of confusion, let's talk about the name.
Yes.
Because I feel like for the first few months, nobody knew what to call this thing. It was the coronavirus, the Wuhan virus, 2019, and COVID.
Nomenclature in science is actually a really serious business. You're right. Initially, it was just Wuhan pneumonia or Wuhan coronavirus. We have a habit of doing that.
Sure, Lyme disease is named after Old Lyme, Connecticut. Ebola is named after a river.
Exactly. But we've learned there's a lot of collateral damage that comes with that.
So why did we stop?
Because of the stigma. In 2015, the World Health Organization issued a new set of guidelines, specifically for naming infectious diseases. The goal was to avoid names that stigmatized geographic locations or animals or specific groups of people.
Right. If you call it the Wuhan virus, you stigmatize the people of Wuhan. It hurts their economy, their tourism, their people, even if they did absolutely nothing wrong.
Or animals. Remember swine flu?
I do, and people stopped buying pork.
Exactly, even though you cannot get swine flu from eating cooked pork.
Yeah.
The name itself caused economic devastation for farmers for no scientific reason at all. So they needed a neutral, descriptive name.
So on February 11th, 2020, the WHO announced the official names. Let's break them down because I think people still get the two confused sometimes.
It's an important distinction. The virus itself is SARS-CoV-2.
Okay, what does that stand for?
Severe Acute Respiratory Syndrome Coronavirus 2. The name indicates that it's a genetic cousin of the original SARS virus from the 2003 outbreak.
And the disease, the sickness you actually get from the virus, is COVID-19.
Which is an acronym. KO for corona, VI for virus, D for disease, and 19 for 2019, the year was first identified.
Simple. COVID-19. It's definitely cleaner than 2019 uncov acute respiratory disease, which was the mouthful they were using before that.
And it successfully divorced the name from a specific place, which is absolutely crucial when you need global cooperation to fight something.
Okay, so we have the name, we have the timeline pushing back into late 2019. Now let's get into the beast itself, Section 2. The biology of an invisible enemy.
Right.
What made this particular virus so good at shutting down the entire world? Why was this so different from SARS or MERS?
It was a perfect storm of transmission mechanics. I mean, a truly perfect storm. Initially, the public health advice was heavily focused on droplets and fomites.
Fomites, so surfaces.
Surfaces, exactly. Remember wiping down your groceries.
Oh, I remember leaving my Amazon packages in the garage for 3 days to decontaminate. We were scrubbing our mail with Clorox wipes. It seems kind of crazy now.
And while surface transmission is, theoretically possible, the data now shows overwhelmingly that the primary driver was airborne particles, aerosols.
This was a huge, huge shift in understanding, wasn't it? Can you explain the difference between a droplet and an aerosol for us?
Sure. Think of a droplet like a tiny projectile. If I sneeze, a big droplet flies out, but it's heavy. Gravity wins, and it falls to the ground within a few feet.
Okay.
But an aerosol is microscopic. It's so small and light that it doesn't just fall. It behaves like smoke.
Smoke is a great analogy. If someone is smoking a cigarette on the other side of a room, you can smell it everywhere, even if you're 20 feet away.
Precisely. And that was the terrifying realization. If the virus hangs in the air like smoke,
Yeah.
it means being in a poorly ventilated room with an infected person is a high risk, even if you stay 6 feet apart.
So all that tape on the floor of the grocery store?
It helped with droplets, but it didn't do anything for aerosols. It meant that ventilation opening windows using air filters was infinitely more important than scrubbing your apples.
And the symptoms, they weren't just the standard flu stuff. I mean, sure, there was the fever, the fatigue, the cough, but there was that one symptom that was so weirdly specific.
The loss of smell and taste, anosmia, and ageusia.
It became the telltale sign. You'd hear from friends, I think I have it. I can't taste my morning coffee. It just tastes like hot water.
It was reported in up to 88% of cases in some of the early studies. It really distinguished it from the flu or the common cold. We learned the virus directly attacks the supporting cells in the nose that help your neurons detect scent.
But the real superpower of this virus, if you want to call it that, wasn't about the people who lost their sense of smell. It was about the people who felt nothing at all.
Asymptomatic spread. This was the Trojan horse of the pandemic.
How so?
With the original SARS in 2003, people were generally most infectious when they were very, very sick, when they were coughing, with high fevers.
So you could identify them. You see a sick person, you isolate them. Problem solved, more or less.
Exactly. You could effectively stop SARS with thermometers at airports. With COVID-19, people were shedding the virus, breathing it out, for days before they had any symptoms. Or, in many cases, they never developed symptoms at all.
So you could feel perfectly fine, go to a dinner party, have a great time, and have no idea you've just infected everyone at the table.
That is what made it impossible to stop at the borders. You can't use a thermometer to check someone who doesn't have a fever yet. The enemy was invisible.
And on top of all that, the virus didn't stay still. It evolved.
Viruses mutate. That's just what they do to survive. It's natural selection on hyperspeed. And this brings us to the variants.
The Greek alphabet soup. Alpha, beta, gamma.
And again, you'll note the naming convention. We stopped using the stigmatizing country names like the UK variant or the South African variant and switched to the neutral Greek letters.
And there were two big shifts in that alphabet that really changed the game, right? The first was Delta.
Delta was a real turning point in terms of severity. It emerged, and it showed us that the virus could actually get meaner. It was significantly more transmissible than the original strain, and it hit people a lot harder.
That was the variant that really strained healthcare systems to the breaking point.
Absolutely. We saw it in India and later across the West. It was brutal. And then, just when we thought we were getting a handle on Delta, came Omicron. Omicron appeared in late 2021, identified in Botswana and South Africa. And it wasn't just another step in evolution. It was an evolutionary leap. It was so much more infectious than Delta. It just spread like absolute wildfire.
I remember when Omicron hit, it felt like everyone I knew got it within the same 3-week period.
That is completely reflected in the data. Omicron became the dominant lineage incredibly quickly, and it spawned all these subvariants like BA.1 through BA.5.
It seemed less severe, though, for many people.
On a case-by-case basis, yes, it often was. And that was partly due to the massive wall of immunity we had built up from vaccines and prior infections. But the sheer volume of cases was so overwhelming that it still put immense pressure on hospitals.
This brings us to the numbers game. The source material mentions R0 or R0. Let's break that down.
The basic reproduction number. It's a key concept in epidemiology. It represents the average number of people that one infected person will pass the virus on to, assuming a completely susceptible population with no immunity.
And in the beginning, we thought this number was pretty low, didn't we?
Deceptively low. The initial estimate back in January 2020 put the R0 somewhere between 1.4 and 2.5.
Which is bad, but it's in the same ballpark as the seasonal flu. It seems manageable.
Or so we thought. But subsequent analysis, once the real-world data really started pouring in, suggested the R0 was actually much, much higher, closer to 5.7.
5.7. So one person infects almost 6 other people.
And then those 6 infect 36, and those 36 infect over 200. That is the math of explosive exponential growth. If your R0 is near 6, you are not dealing with a campfire. You are dealing with a wildfire in a dry forest. You cannot stop it with half measures.
So we have a highly contagious airborne virus that spreads before you know you have it, and it multiplies exponentially. No wonder the world just hit the brakes.
Yeah.
This leads us right into Section 3, the global STARP and the response.
It was an incredible moment. The response was unprecedented in human history.
Yeah.
And we saw two main competing philosophies emerge on how to handle this wildfire.
Suppression versus mitigation.
Or, as most of us knew them, zero COVID versus flattening the curve.
Let's start with zero COVID.
Zero COVID was the strategy of complete elimination. Think of China or New Zealand in the early days. The goal was to get cases down to zero and keep them there through incredibly strict border quarantines, mass testing, and immediate snap lockdowns if even a single case appeared.
An eradication strategy.
Exactly. And then you had flattening the curve, which was the strategy for most of the rest of the world.
What was the thinking there?
It was a tacit admission that we probably couldn't eliminate it. It was already too widespread by the time we acted. But the goal was to slow it down, to spread the infections out over a longer period of time so that our hospitals wouldn't completely collapse under the strain.
And the main tool for both of these strategies was the lockdown.
The lockdown. By April of 2020, just a few months in, more than half of the world's population, that's 3.9 billion people, were under some form of lockdown. A global pause button had been pressed.
And the silence. I remember the silence in the cities. The source material has a term for this, the anthropause.
It's a fascinating term, isn't it? A temporary but massive drop in human activity.
And the environment reacted almost immediately, didn't it?
It was stunning. We saw a 26% drop in coal consumption in China. NASA satellite imagery showed nitrogen dioxide levels, that's a major pollutant from traffic and industry, just plummeting over major cities. The skies literally cleared up.
It was more than just clear skies, though.
Oh yeah. Seismometers, the instruments that measure earthquakes, actually picked up less vibration from the Earth's crust because there were fewer cars, trucks, and trains moving around.
The Earth literally got quieter.
It did. But while the skies were clearing, the global economy was crashing. It was the largest global recession since the Great Depression. It wasn't even close, and supply chains just shattered.
I think everyone remembers the panic buying.
The toilet paper.
The toilet paper, the canned goods, the flour.
The toilet paper was the visible symptom of the problem. But the real crisis was invisible in things like semiconductor chips.
Right. Suddenly you couldn't buy a new car or a gaming console or even some home appliances for 2 years.
That supply chain chaos was a direct result of that global stop. We all learned how fragile our just-in-time economy really was. We had traded resilience for efficiency, and when the system broke, we had no buffer.
And for those of us lucky enough to keep our jobs, the very location of work changed forever. The explosion of telework.
Remote work? It went from a niche perk for some tech companies to the standard operating procedure for millions overnight.
It completely changed the definition of the workplace.
It did. And we're still seeing the ripple effects of that in 2026.
Yeah.
With the crisis in commercial real estate and the decentralization of cities.
But while we were all sitting at home baking sourdough and trying to find a webcam that wasn't sold out, the scientific community was running the race of a lifetime.
The vaccine.
This really is the bright spot in the data.
It's an incredible story. The speed was just unbelievable.
Yeah.
Usually, vaccines take years, sometimes a decade or more. The mumps vaccine was the previous record holder at 4 years.
4 years. And for COVID.
We had multiple vaccines being rolled out in December 2020.
Yeah.
That is less than a year after the virus was even identified.
How is that even possible? I remember so many people being skeptical, saying it was rushed, that corners must have been cut.
It wasn't magic, and it wasn't rushed. It was prepared science. The development was massively accelerated by all the existing research on the original SARS and on MERS.
So scientists had already been studying this family of viruses for years.
For decades, they knew the spike protein was the key, the target. And crucially, they had been working on mRNA technology for a very long time. It was a platform just waiting for a purpose.
So they had the DVD player ready, they just needed to pop in the new disc.
That is a perfect analogy. As soon as the genetic code of SARS-CoV-2 was published online in January 2020, they essentially downloaded it and plugged it into their existing mRNA platform. They had the design for the vaccine within days.
And the rest of the time was just testing.
Testing for safety and efficacy. The trials were huge and rigorous, but they were run concurrently instead of sequentially to save time. No steps were skipped, they were just overlapped.
And the impact, we have hard numbers on how many lives were saved?
We do. The estimates suggest that vaccines from Pfizer, Moderna, AstraZeneca, and others saved between 14.4 and 19.8 million lives.
Wow.
And that's just in the first year of the rollout. Nearly 20 million people are walking around today because of that science.
That's incredible. That's the population of the entire state of New York. But we can't talk about the triumph of the vaccine without talking about the inequality.
No, we absolutely can't.
Yeah.
It was a major moral failure of the global response. We saw what many people called vaccine apartheid. Meaning high-income countries were buying up all the supply, they were vaccinating healthy teenagers and children, and talking about second boosters, while low-income nations were struggling to get even a first dose for their frontline health workers and their most vulnerable elderly citizens.
It highlighted the global divide in a very stark, very painful way.
It really did.
So we have the virus, the lockdown, the vaccine. Let's look at where we are now. Section 4, the aftermath and the end.
And that question of when does a pandemic end is actually a very complicated one.
I think we were all waiting for some kind of V-Day declaration, like the end of a war, a big announcement, but it never really came.
Well, on May 5, 2023, the WHO did declare that the public health emergency of international concern was over. But, and this is the crucial part, they explicitly stated that the pandemic was not over.
That feels contradictory. How can the emergency be over, but the pandemic isn't?
It highlights the definition problem. There is no biological on-off switch where the virus just vanishes from the earth. It transitions to what we call endemicity.
Meaning it becomes part of the furniture.
Exactly. Like the seasonal flu or the common cold, it's always there, circulating at some baseline level.
So the end isn't a biological event.
Experts note that the end of a pandemic is often a social phenomenon, not a biological one. It ends when society collectively decides to accept the risk and get back to normal life.
So the virus is still there, it's still making people sick, it's still killing people, but we stop treating it as an all-consuming emergency.
The panic ends, even if the disease doesn't.
And for many, many people, it hasn't ended at all because of the long-term scars.
Yeah.
We have to talk about long COVID.
This is the lingering shadow of the pandemic. Long COVID is defined as consequences that persist long after the initial recovery period. New or returning health problems that can go on for months or even years.
How prevalent is it? How many people are we talking about?
The estimates vary wildly, which just shows how much we still have to learn. But studies suggest it affects somewhere between 5% and maybe as high as 50% of patients who get infected.
That is a massive range. But even at the low end, at 5%, that's millions and millions of people.
It's a mass disabling event. And the symptoms are just debilitating. Crippling fatigue, shortness of breath, heart palpitations, and this cognitive dysfunction people call brain fog.
Brain fog, yes. People struggling to find words or concentrate.
We're seeing people drop out of the workforce because they physically cannot do their jobs anymore. We are still trying to quantify the economic and social cost of this.
And it's not just physical health. The mental health toll was global.
Absolutely. We saw global increases in anxiety and depression across the board. And there are other long-term ripples, like this idea of an immunity debt or immunity gap.
Right, the triple-demic we saw a couple of winters ago.
Exactly. Because we were all isolated for so long, our immune systems weren't getting their usual workout. We missed our routine exposures to other bugs like RSV and the flu.
So our immune systems were out of practice.
They were. So when we finally opened everything back up, all of these viruses that had been suppressed came roaring back and hit us all at once.
We also saw a drop in routine vaccinations for children for things like measles. We're still playing catch-up on that.
The tail of this pandemic is very, very long.
So let's try to summarize this deep dive. We lived through a genuine historical pivot point, the 5th deadliest pandemic ever recorded.
It completely reshaped our economies. It normalized remote work for a huge portion of the population, and it advanced vaccine science at a record-breaking speed.
But it also exposed these deep vulnerabilities in our supply chains, in our healthcare systems, and in our social equity.
And it showed us, in no uncertain terms, that biology does not respect borders.
And here's the thought I want to leave you with today, pulled from our source material. It mentions that an epidemic's end is often a social phenomenon, not just a biological one. So if the virus is still circulating, still killing thousands of people, still disabling people with long COVID, have we actually beaten the pandemic, or have we just collectively decided to stop paying attention to it?
That is the uncomfortable question, isn't it? Are we actually safe, or are we just tired of being scared?
Something to chew on. Thank you for listening to this deep dive into the COVID-19 pandemic. Stay curious, stay safe, and we'll see you next time.